Hello everyone! Welcome to this video where we'll explore tokenization and embeddings. These are fundamental concepts for working with text data in neural networks. Tokenizers help prepare text for neural networks, while embeddings convert text data into numerical features that neural networks can process. We'll be using resources from Hugging Face for our demonstration. In this video, we'll use Google's BERT model as our example. BERT stands for Bidirectional Encoder Representations from Transformers, and it's a powerful model described in a research paper. This model can perform impressive tasks like predicting missing words in a sequence and even predicting the next sentence after a sequence of sentences. You can check out BERT on Hugging Face, which is a great resource where you'll find not just BERT models, but also many derivatives and related models. Let's begin with a hands-on exploration of tokenization. Since neural networks operate on numbers, we need to convert text into numerical tokens. That's exactly what tokenizers do. We'll use the PyTorch library to make this process easier, pulling from the PyTorch hub to access the BERT-based model with capitalization. This means our model will be case-sensitive, handling uppercase and lowercase letters differently. Tokenizers can encode multiple texts at once, which improves efficiency, but let's start with a simple example to understand the basics. It looks like we need to install a dependency first. Let's run a quick pip installation to fix this runtime error. Now we can proceed with tokenizing our text. When we encode our text, we'll add special tokens which are inserted at the beginning and end of the sequence. Looking at the result, we can see a special token at the beginning, another special token at the end, and several tokens in between. Most of these tokens correspond to individual words, but for unusual or compound words like quadratical, we get some interesting token representations where the word is broken down into multiple parts. We can also decode our encoded text directly using the tokenizer's decode method, which converts the tokens back into readable text. To use the BERT model for predictions, we also need a list of segment IDs. This is a vector with the same length as our tokens, representing which segment each token belongs to. Since our tokenizer added special tokens, we can use these special tokens to identify the segments. First, let's define which index corresponds to which special token. The CLS token used at the beginning has an ID of 101, and the sep token, the separator, has an ID of 102. Next, we'll create a function with a loop that starts with the segment ID set to 0 and increments it whenever we encounter a separator token. We'll return both the segment IDs and index tokens as tensors since we'll be feeding these into the model later. Let's test our function to make sure each number correctly corresponds to the first and second sentence segments. Now, let's talk about text masking, an important concept for training word embeddings. BERT masks out a word in a sequence, replacing it with a special mask token. We can see this special token by using tokenizer.mask token, It has an ID of 103. Let's take our previous sentences and mask the word at position index 5. We'll apply the mask and verify that it appears in our sequence of tokenized sentences. Now comes the exciting part, predicting the missing word. For this, we'll load a model using PyTorch Hub and Hugging Face. Let's also examine the architecture of this model to understand its structure. Now we can proceed with making predictions. Since we're just performing inference and not training the model, we don't need to calculate gradients. Let's look at the shape of our output. We have our number of tokens, our batch size, which is just 1 in this case, and the predictions for each token across BERT's entire vocabulary. With outputs like this, we need to apply a softmax function to convert these values into probabilities. Our predicted index is 1241. When we convert this to a token, we get the word both. So our masked sentence becomes, I understand equations, both the simple and quadratical. That seems like a good prediction given the context. Let's wrap up this section by exploring question answering capabilities. We can reuse our previous text, but we'll need to load a new model specifically designed for question answering. We'll load this from the PyTorch hub as well. For more details about these models, you can always check Hugging Face. The model we're using here is a larger BERT model that doesn't use capitalization or case sensitivity, and it's been fine-tuned on the squad dataset, which is designed for question answering tasks. Let's proceed with tokenizing our text and loading our question answering model. Once the model is loaded, we'll perform inference, again skipping gradient calculations since we're not training the model. The question answering model works by scanning through our input sequence to find the subsequence that best answers the question. The model produces start logits and end logits. The higher the value in start logits, the more likely that position is the start of the answer. Similarly, the higher the value in end logits, the more likely the answer will end at that position. We'll use argmax to find the most likely start and end positions, then extract the answer sequence from these positions. With a final decode of this sequence, we'll get our answer quadratical. That concludes our introduction to tokenization, embeddings, and how they can be used for tasks like masked word prediction and question answering with the BERT model. If you'd like to support the channel, consider starting a free trial of our new design tool, which is linked in the description, and let us know what you think. If you have any questions, please post them in the comment section and we'll do our best to respond. Thank you very much for watching to the end, and please enjoy responsibly.